Okay, Chem1110 students, we are going to start talking about molecular geometry. This follows directly from the Lewis structures we were doing in Chapter 7. And the whole point of molecular geometry is to figure out the shape of the molecule, because for chemical reactions to occur, two molecules have to collide. Old bonds are broken, new bonds are made, and so it's important that the parts where bonds are being broken and made actually collide with one another. And so we want to know about the shape of the molecules, and the most useful model so far is this valence shell electron pair repulsion model. And so the molecules we're talking about are ABX, where the central atom is A and it has some B atoms around it, either 2 to 6. Here's an example in this table of the kind of molecules that we are talking about. And in the VSEPR model, the key is that electrons repel each other. Electrons are all negatively charged, and like charges repel. And so the electrons in a molecule are going to arrange themselves so they can be as far away as they can from each other in order to minimize repulsive interactions. So this, remember, is going to be lone pairs of electrons as well as the electrons that are in a bond. And so I have some pictures here that demonstrate this. The one on the left would be an AB2 molecule, maybe something like CO2, where you only have two bonds and the electrons are trying to be as far away from each other as they can be. There are no lone pairs, and so it becomes a linear molecule. They're 180 degrees apart. The one to the right is something like boron trihydride, BH3. You have 3 bonds between the boron and the 3 hydrogens, no lone pairs, and so those 3 bonds spread out as far as they can, and they are pointed towards the corners of a triangle. The next one's 4 electron domains. This would be like methane, CH4. So you have 4 bonds, no lone pairs of electrons. And those, when they spread out in space as far as they can, that's called a tetrahedral diagram or arrangement. If you have 5 electron bonds, you get a trigonal bipyramidal. So you have 1 on the top, 1 on the bottom, and 3 is sitting in a plane around that central atom A. And since there's 3 of them, they push as far away as they can from each other. So that makes a triangle, and 1 above and 1 below means it's like 2 triangular pyramids that are put together base to base. If you have 6 electron domains, so that central planar structure has 4 electron domains, and so it's like 2 square pyramids stuck base to base, but we call this octahedral. All right, so if we want to compare electron domain geometry and molecular geometry, they are quite often different, because electron domain geometry is the arrangement of the electron domains. So now we're looking at lone pairs of electrons as well as the electrons in a bond. And yet when we look at molecular geometry, we're just looking at the arrangement of the atoms. And the way I like to think about this is that I can't see the electrons. So the electrons are dictating where things are, but I can't see them. All right, in talking about this, we want to look at bond angles. And so that's going to be the angle between adjacent AB bonds, with A being the central atom. And so I have the 5 arrangements I just talked about. In a linear molecule, you're going to have a 180 degree angle because it's straight. In the trigonal planar, those B atoms are sitting at the corners of a triangle, so it's 120 degrees between those angles. Tetrahedral is kind of interesting because it's not a shape we're used to, and that's 109.5 angle. like I say, like methane. Then we have the trigonal, bipyramidal, and the octahedral, and I want to look at this trigonal bipyramidal a little bit more because here you have two different bond angles. Remember, you have an atom on top, an atom on bottom, so those are 90 degrees away from the plane, but the plane that contains the 3B atoms make up a triangle, so you have 120 degrees there. All right, so we're going to look at the electron domain geometry versus the molecular, and the key is we have to look at the lone pairs that affect the electron domain geometry or define it, but there are just electrons, so you can't see them. So now the molecular geometry is not the same. And I have an example here of ozone. If you draw the Lewis structure for ozone, this would be one of the predominant molecular structures, and you see our central atom, which is oxygen, has a lone pair of electrons on it. So you have to have 3 electron domains, 2 for the bonds. One of them is a double bond, and then you have to have a place or space for that lone pair of electrons. And so that's a trigonal planar arrangement when you look at the electron domains. But when you just look at the atoms and you can't see those lone pair of electrons on the top, the atoms are bent. And we call that a bent geometry because it looks like we took something linear and bent it down. And in fact, those electrons in the bonds have been pushed down. So I have a fairly big chart here. It's on 2 different sheets, but what it does is it takes the number of electron domains and the number of lone pairs and determines the electron domain geometry and lets you see where the lone pairs are and then the resulting molecular geometry. So the first line is like what we saw with ozone, because you have 3 electron domains, but one of them's a lone pair, and so you end up with a bent molecule. In the next one, the example is ammonia, NH3. And when you work out the Lewis structure, you see there is a lone pair of electrons. And so you have a central atom, which would be the nitrogen, 3 hydrogens around it, and then a lone pair of electrons. And you can see that in the 5th column. However, when you're just looking at the molecule, you can't see that lone pair of electrons. And when you just look at the atoms, it looks like a tetrahedral where the top atom is chopped off. And so that's called a trigonal pyramidal. It's like a triangular pyramid. And water is an interesting one, 4 electron domains, but that's because there are 2 lone pairs of electrons on the oxygen. Once again, it's tetrahedral, but 2 of those tetrahedral slots are taken up by the lone pairs of electrons on oxygen. So when you realize you can't see them, you once again get a bent structure. Here's some other ones. This is where you have total electron domains of 5 and 6 with varying numbers of lone pairs, and the resulting molecular geometry you get. Now there's a couple here that are kind of strange. One's called seesaw, one's called T-shape, and I've been asked if you have to memorize all these, and my answer is you need to know the bent. You need to know the square planar. You need to be able to go from electron to main to molecular geometry, but I'm not going to ask some of those strange ones like seesaw and T-shaped. All right, moving on. So we're comparing electron domain geometry and molecular geometry, and so here's a series of steps. You draw the Lewis structure, you count the number of electron domains. Here you use VSEPR, and you determine the electron domain geometry, and then you consider what the position of the atoms are, knowing you can't see the electrons, and that gives you your molecular geometry. So I have an example of two molecules, SO3 and ICl4 minus. So that's an ion. And we're going to compare the VSEPR model, or the electron domain geometry, and the molecular geometry. So for SO3, sulfur with 3 oxygens around it, you have an electron domain that looks like a trigonal planar. There are no lone pairs of electrons, and so the molecular geometry looks the same. It's trigonal planar because those 3 oxygen atoms spread out as far apart from each other as they can. When we look at the ICl4 minus, there are 6 electron domains, all right? So you have to have 4 for the chlorines, but there are 2 non-bonding pairs of electrons on iodine. Draw this one out so that you can see this. Draw your Lewis structure. And so those electron domains, or those lone pairs of electrons, are going to be at the top and the bottom because they are just naked electrons. They're going to be as far away from each other as they can be. So the atoms end up being in a square planar geometry. All right, there are some deviations from the ideal bond angles, and that is, the bond angles we expect are due to equal repulsion of the neighboring domains, but lone pairs do take up more space. As I just alluded to, there's not an atom on the other side with protons pulling the electrons. They're just bare electrons, so they take up a lot of room. Multiple bonds, because a double bond contains 4 electrons, is going to repel a little bit more strongly than a single bond, which only has 2 electrons in it. So it's going to push a little bit more. And so this geometry often helps you determine molecular polarity, and we've already talked about how polarity is important. And so I have some examples here. Ammonia, the angle, it came from a tetrahedron, 109.5, but we get 107 instead. Those bonds have been pushed down a little bit harder. The next one is SF4, and where we expect it to be 180 degrees from the top to the bottom, it's 173. It's gotten pushed harder by that lone pair of electrons on the sulfur. The next one is bromine pentafluoride. Non-bonding pairs of electrons on that bottom of the bromine push the other ones up. And then we have formaldehyde. Once again, it's a double bond that is pushing this. So instead of 120 degrees each, the hydrogens get closer together, so you get 116 on that bond angle. And where that double bond is pushing further away, instead of 120, you get 122. All right, so that's the end of the first part of Chapter 7, which is going to be included on Exam 2.